Hi, this is Christopher Boucher, and I'm going to review how to do a hypothesis test with a z-distribution with one tail. It's one of the easier types of hypothesis tests. Okay, we'll get started here. The average annual salary for a starting plumber in the United States is $40,000, with a standard deviation of $500. A sample of 32 new plumbers shows an average annual salary of $40,200. Based on this data, our new plumbers earning significantly more than expected. So a couple things here I have underlined more, so the more is important. And when we take a look at this information here, we have our sample, which is 32. We're going to assume it is normalized, or the sample is large enough. And the other thing is we have a population standard deviation, because it says right off the bat what the average is in the United States. We're assuming that's the population mean, and then this is the standard deviation right after it. So this is the standard deviation for the population. So, okay. Our null hypothesis to start off with, let's write everything out. Our null hypothesis is always going to be the status quo, which is mu is 40,000 or less. You always do or less if we're trying, if the alternative hypothesis is going to be more. So our alternative hypothesis is more, as is underlined right here. So our alternative hypothesis is going to be mu is greater than 40,000. So it's always based on the mu, or the population mean, these numbers right here. It looks like you'd want to put in here 40,200 down here for the alternative, but that's not what you're doing. You're trying to see if the status quo or the null hypothesis is either we're going to reject it or not reject it. So that's the whole crux of what we're doing. Okay, and the population mean is 40,000. And our standard deviation is right here, 500. And our sample mean is 40,200. And our n, which is a little n, is our sample size, which is 32. Okay. So we have our information listed here. Oh, and one other thing, we're going to perform the test to a 2.5 level of significance. So that's important. That's essentially our alpha. Okay. So let's draw a picture. With hypothesis tests, I always recommend drawing the picture. Even though you can do these on the calculator, we want to draw the picture. Not a very good artist, but that's okay. Okay, so we draw the picture, and mu is right here, and it is our 40,000. Okay, so the area of interest that we're looking for, that we're looking to see if our test statistic gets inside of, because we're going to use the rejection method, is on the left or right of this. So the area of interest is always identified by the direction of the alternative inequality, alternative hypothesis inequality. So right here. So it's pointing to the right. So what that means is our rejection zone is right here. We can make this a little longer if we want, but it's this side right there. Okay, so we know this is our rejection zone. So if our test statistic gets inside this area, then we are going to reject the null hypothesis. If it does not get inside this area, then we are going to not reject the null hypothesis. Okay, So let's go on and do some calculating here. So the first thing that I'd like to do is find the test critical value for our 2.5% level of significance. So to do that, we're going to get out our Z table. This is a modified Z table. But we're looking for the 2.5 level of significance, and that is equivalent. Let me zoom in. That is equivalent to 1.96 on the for the Z-score, 1.96, and this is what the value is under the curve. But the actual Z-score is 1.96. People always ask me, well, how do we get this information? Well, if we take a look at this now, this, like I said, this Z-table is an alternative Z-table, which is not a right table, left table, or cumulative. It's just one side. So it starts at 0 and it goes all the way up to almost 0.5. So it's just one-sided. But the way that we get this is this right here. So we're looking for 2.5 alpha. So 2.5 alpha on a one-tail hypothesis test. We need to find the place where it is 0.475 on the table. And then if we add what the other side would be, 0.5, then we're left with an area that is our beta, which is 97.5, and then our alpha, which is 2.5, which is what we want, %. So that's how we come up to this number where our Z value is, Z-score is 1.96. And so that is, and this is for the rejection method. So this right here is 1.96. That's the critical cutoff for our test. I'm going to back it off now. Okay. So now let's do the calculation based on our sample data. And we're going to do that like this. Use the Z distribution formula, which is okay. So let's see. So our X bar is 40,200, and our mu is 40,000, and our standard deviation is 500, and our n is 32. Okay, so I've worked this out in the calculator. You need to trust me in this part. Our answer is 2.262. Okay, so now we need to figure out where this goes. So when we're looking at this right here, our distribution, it goes, and the actual Z-score gets larger as we get away from the mu, or the center of the distribution. So as we go out, the Z-score values increases, and of course the Z-score values are a representation of standard deviations away from the mean. So when we go and we look at 2.262, we understand that it is inside of our rejection zone. So we would reject the null hypothesis, and we would say we reject HO, or H0, our null hypothesis, and we would say that it appears that the plumbers in the United States may be making more than 40,000, but we would have to do more testing. So in this case, we would reject the null hypothesis, and then we want to keep doing tests to see. And to see if it's actually true. If our value was inside of this non-shaded area, then we would what they say, do not reject the null hypothesis, which would make us think that the status quo is correct, which is plumbers in the United States are making $40,000. Let me make sure that I got everything covered. Oh, and one thing that I usually do that I skipped real quick was the how we determine which distribution we're going to use. And I think I mentioned it, but what we do is we do, if we have a known sigma, that's one key with the z distribution, and then our n is greater or equal to 30, which makes us really inclined on using the z distribution. It's a gimme using the z for that. Okay, thank you.